Welcome to COLLOQUIUM today. We have with us Professor Sarita Vig. Pleasure to introduce her. He is a professor at the Indian Institute of Space Science and Technology, Thiruvananthapuram. She completed a PhD from IIST in 2005, where after which she did a postdoctoral stint at IIST Observatory, Florence, Italy, till 2008. She was also the PI of a project at IIT Madras till 2010, after which she joined IIST. Her research interests include massive star formation, galaxy clusters, interstellar medium, and galaxy structure. She teaches astrophysics to students pursuing the bachelor's and master's at IIST. And she's very interested in astronomy outreach. She loves to talk to people about cosmos. So today she'll be telling us about star formation. And she also told me that she'll talk about interesting things like jets. Yes. And Protostellar does. So looking forward to the talk. Welcome.
Yeah, thank you, Pallavi. So first of all, before I start off, I would like to thank ICTS for inviting me. And I'm going to talk, I work, as you know, in the area of astronomy, astrophysics. And today I'm going to give a brief introduction to this topic and also move on and explain some things about what we do. So I'll start, I have started it from a level where people who do not know much about astronomy can also take away some bit. So the plan of my talk is as follows. I will first talk about interstellar medium, then I will talk about molecular clouds, which are the birthplaces of stars, and the process of star formation, pinpointing the location of young stars, how to find these star forming birth sites in molecular clouds, and how you move in, when you move in close, zoom in, what do you see? What are the currently open problems which are present, which we are trying to understand and solve? And finally, towards the end, before I summarize, I will talk a little bit about JWST, which is actually a boon for us in the area of star formation because it can throw or shed a lot of light towards the open problems that I'm going to talk about. So what is interstellar medium? So if you look up at the night sky and you look at the stars, then between the stars, you see that you don't see much, right? And it seems to be empty space, but it is not really empty. It is actually made up of a medium which is mostly gas and some very, very tiny particles, few tens to few hundreds of nanometers in size. These are the dust particles. So this medium which is present between stars, which is made up of around 99% gas and 1% of dust, is known as the interstellar medium. And this is what you see when you're seeing pictures of nebulae, which I'm sure you have seen. This is what is radiating, this medium is radiating, this is the interstellar medium. And this interstellar medium, of course, is not homogeneous. It is distributed very unevenly. And secondly, it is not static also. It is not the same. It is going to change with time. And because of this, what astronomers, astrophysicists do is they try to categorize this interstellar medium into various phases depending on the density, temperature, and so on. So the various phases of the interstellar medium are as follows. This is broad categorization of how you will distinguish the different phases. The most densest phase is the molecular phase, and then you have the neutral phase, and then you have the ionized phase. So obviously it has to do with some specific element that we are talking about, and that is obviously hydrogen, because 70% by mass of the universe is hydrogen, and that is why the interstellar medium classification is also based on this. So the phase where hydrogen is in molecular form, if it is very dense and therefore occupies a very small volume, it is dense at low temperatures. As you can see, this is the density, this is the temperature, very, very low temperatures, 10 to 30 Kelvin and so on. And this is the total mass in our galaxy. So this M, and this is the symbol for sun. So that is solar mass. So this is typically around 2 billion solar mass in our galaxy. That much mass of the ISM is present in the molecular phase. And obviously, since this is very dense, then it will occupy a very, very small fraction of the volume. And that is given by this quantity F. Then we have, I'll go to the cold neutral medium. This is the neutral medium where hydrogen is in neutral form. And here again you can see that what are the typical densities, temperatures that people have measured, and what is the fraction of the volume. These are typical numbers that people estimate statistically. And then you have the warm and hot ionized phase. When hydrogen is in ionized form, this is because of the ionization due to radiation from stars. And that, as you know, since it's a very hot phase, the gas expands, it occupies the largest fraction of the volume. It has a very high temperatures can reach as high as few million Kelvin in some places, but the number density is very low. So these all phases are held together because of pressure equilibrium, and this picture in fact kinds to summarize this, where you can see the dense clouds. This is the and then you can have very hot phase or warm ionized phase or hot ionized medium, very close to a very explosive event like a supernova, as you can see here. And then in regions where there is not much radiation, for example, you can have gas condensing and forming these molecular clouds. Now, how do you detect these various phases? As I said, we use hydrogen to detect them. So for molecular phase, in this phase, molecular hydrogen is present in molecular form, but it's very difficult to detect molecular hydrogen. I'll be coming to this aspect. Here it is through the hydrogen is in atomic form. So we use the 21 centimeter line of hydrogen because this is relatively cooler. We use this line to detect this phase. And for warm ionized medium means the hydrogen is ionized. You have plasma of electrons, protons. In this phase, this plasma phase, where you want to detect this medium, we generally use radiation from at longer wavelengths such as radio, because of certain physical processes like Bremsstrahlung and so on that these electrons undergo, thermal Bremsstrahlung. I won't go into those details. What I will be focusing on now is the molecular phase, because this is the birth site of star formation. Now, detection of molecular clouds. How do you detect molecular clouds? If you wanted to detect molecular clouds, what would you do? So as I said, we can use molecular hydrogen, but molecular hydrogen being a homonuclear molecule, it does not have permanent dipole moment. So it only has quadrupole rotational levels, and even these rotational levels are at where the energy spacing is very large. Consequently, you can't use them unless they get excited to those high energy levels, and for that you need different kind of conditions. You need high temperature conditions for this, or a lot of collisions for this to happen. So you cannot use this to sample, for example, the cold neutral phase where the temperatures are really low. A proxy which is used to detect molecular clouds is the second most abundant molecule which is present, which is carbon monoxide, or CO. Now CO has multiple advantages in the sense that the lowest, it has a very nice dipole moment, and as a result the lowest energy level is around 115 gigahertz, and which is in radio. So you can use the transitions in radio to detect these molecules, CO molecules. And CO is more or less found in all the regions where you would find molecular hydrogen. But if you are detecting CO, how do we get the amount of molecular hydrogen that is present there? For that we use empirical relations. We based on abundance conditions, how much hydrogen is there vis-a-vis how much carbon, and some astrochemistry also we put in together, and based on that we get some kind of relations like this, which relates, for example, the density of molecular hydrogen is related to the density of carbon monoxide. And as you would anticipate, carbon monoxide is lower in density, around 10,000 times lower. So this is an empirical relation, and which is used very often, but at the same time this is also an area of research where people are working on, because this is not hard and fast, and this number may not be constant in different parts of the galaxy. People are trying to determine this relation also. Okay, oh, in the picture, sorry, I should explain the picture as well. In this picture, what you see is the Orion constellation, right? And what is, this is an optical picture, and on top of that is overlaid, along with the optical is overlaid this region. If I had to see in the line of, that is, I am looking at the spectral emission from the carbon monoxide molecule. So I am looking at this region to see where carbon monoxide molecule is emitting, and from that I can detect where the molecular cloud is in this region. But this is in projection, mind you. So this, when I look here, I see that what you see here, this is the M42 nebula. This is where stars are forming, and that corresponds to this. So I don't know if you have really looked up at the night sky and seen Orion, but this is visible with the naked eye, M42, and that is a region where stars are actively forming as well. So this is overlaid on this, and that doesn't mean that this molecular cloud is at the same distance as these stars. These stars are located at very different distances. The constellations are in a, the stars in a constellation are located at very different distances. Now we can use, yeah. See, it has to do with the abundance of all the species plus the temperature plus, so the astrochemistry goes in to find that, see, after you see hydrogen and helium, helium is noble anyway. So then you have oxygen and carbon and so on. And then what kind of chemistry allows you to lead you to the formation of other molecules? And it so happens that the chemistry shows, even astrochemistry, people are still working on formation mechanisms. By the way, I should also emphasize here that although I'm talking about molecular hydrogen, we still do not know 100% how molecular hydrogen is formed. There is, because the density is so rare, I didn't talk about it there, that it is so less dense, you cannot expect one hydrogen atom and another hydrogen atom to come and then collide and form a molecular hydrogen. What usually happens, what people think now is, since there's a lot of tests everywhere, it provides us sites where you can have one hydrogen coming and forming. So molecular CO it is more easily possible. Not as much as molecular hydrogen, but that's more easily possible even in the gas phase. So one needs to see how these are formed, okay? Okay, so now we have talked about detection of molecular clouds, but if I want to see into the molecular clouds, because molecular clouds is the densest phase, and this is the region from where stars are going to form. But I need to look into the molecular clouds. If I can't use CO line, because CO will be emitted from everywhere in the molecular cloud, right? But I need to see somehow into, or if I'm interested behind or something. So what will I use? So what is usually done is, since molecular clouds are this densest phase, it has dust, small teeny weeny particles that I told you about, mostly made of silicates and maybe some iron, maybe some carbides and so on, oxygen and some nickel and manganese and so on. These teeny weeny particles, they are solid state particles. Since they are solid state particles, they are going to absorb the optical light. And therefore, when you look at these regions in the optical light, you will see them like this. Because why is it that you see it like this? Initially, when these were first discovered, people thought they were holes in the universe. You could probably go to a parallel universe, but now we know it's not such a fancy theory. Rather, we know now that the dust is absorbing the background starlight. But then you need to somehow be able to see through it. And that is where infrared comes into picture. Because infrared, these dust particles allow the longer wavelength radiation to pass through. People even characterize how much they allow and so on. Again, I won't go into details. And let me just tell you, in astronomy, very often you will come across these beautiful pictures, right? 3-color pictures. And these need not always represent the actual true colors of those pictures. For example, the nebulae that I showed you. Okay, and even you will see pictures showing beautiful nebulae in X-rays with 3 colors. We know we cannot see we cannot see X-rays. Then how do you do that? What astrophysicists or astronomers usually do is they take the emission of that region in 3 different wavelength bands and they combine them using the RGB colors, okay, which is done here also. So here the emission from this is a cloud known as Barnard 68, and this is combined using 3 filters, the light passing through 3 filters. These are all optical. Okay, this is in blue, this is in visual, visual is somewhere around greenish, and this is towards the reddish side but still optical. Now the same region I am looking in BV, but now I am looking at near infrared, 2 micron. So already you begin to see that a 2 micron light is passing through, and this is not these stars do not represent the stars, in this case at least, which are present within the cloud, rather it represents the background stars. That means light is able to pass through. This nebula has not started undergoing star formation yet, okay? Otherwise, you will definitely see a very strong signature of a star being formed. So this shows that infrared can be used. We use longer wavelength radiation near mid-infrared for in order to probe into the cloud or behind the cloud. And in particular, if you have a young star, then the young protostar around it will start heating up its surroundings, and the dust which is present will start emitting also, which is not yet destroyed but close to it, and that emits again in mid-infrared, longer wavelength mid-infrared. So infrared acts as a, it has double advantages. You can penetrate into the cloud, plus if there is a young star sitting there, you can actually be able to locate these young stars.
There was no star in the foreground of this?
No. This is very small in size. The distribution of stars is that it's 3D, right? But here there is none. No, it's not there. So if you start looking at very small regions of skies, you will see. You need to have really high density of stars to be everywhere. Okay? Yes.
Way of saying that the density profile of carbon monoxide matches with the hydrogen density profile. And wherever there is high abundance of hydrogen, there is high.
Yes, it is found that the conditions which lead to the formation of the conditions under which molecular hydrogen would be formed, with those conditions, higher density conditions, is also where you will find CO. And that goes into this to some extent. As I said, we use a lot because we don't have any other way. But one needs to look at that empirical relation. It's like a foundational relation that we need to look at very carefully, and people have started looking at that now. And they find that it varies slightly, but more or less this is not bad. Let us put it that way. Okay, so it is not, and they do it empirically in the sense they also do from other observations of hydrogen, where you can measure CO, for example, using the higher, because when you are actually using rotational levels, you can use the quadrupole rotational levels in some region. And when you are using those, and suppose you are looking at CO, you will be sampling that cloud, that amount of gas which is present in that phase versus the CO phase. But people use that and then again use some model. So it's not something that we can easily come up with. But people have anyway started to question these relations also. Does it answer your question? Okay. Okay, so this is an example of another region. Now this is a case where we are probing into the cloud and actually seeing a star being formed, as you can see here. So this is an optical, this is it appears like there's a starless core here, but then when you start looking at it in infrared with the Spitzer Space Telescope, because it is very faint, so we needed a space telescope, and then you start seeing that there is something which is in there, which is beginning to appear at mid-infrared wavelengths. Okay. So this is a small animation which shows you the optical versus the infrared. So you are familiar with this nebula, the Horsehead Nebula, yes, and this is the optical, and then as you go, you will see the Spitzer part of that nebula, and you will see how it lights up, all this lights up, which was obscured in the optical. So this is the reason I am showing you this is, I'm trying to emphasize that if you want to study star formation, we need to go to near and mid-infrared in order to look into the molecular clouds. Okay, so yes. Yes, which means that there is no star formation occurring there, and it is really, really cold dust, which is not even emitting at mid-infrared. If you go to far infrared, that dust will start emitting at far infrared. In fact, that region I will revisit when I talk about JWST, okay? But there also we have only the near infrared image. All right, so now I have been saying, yeah, molecular clouds are the birth sites of star formation. That is because when we look in our galaxy, we are seeing young stars being formed in the molecular clouds. But is this true on large scales, on galactic scales, on very, very large scales across the galaxies? So people are doing this study and finding that there is a strong correlation between molecular gas and stars. So molecular clouds are the coldest, densest phase of the medium, as I've already said. And what are the typical masses of molecular clouds that you can see? It's 100 to 100 times the mass of the sun to typically 10 million times the mass of the sun. And there is, as I said, this is at different scales, we are seeing this strong correlation between star formation and molecular cloud. Now, how are we seeing this correlation? So this is, I'm just given an example of a study where they have sampled the star formation using mid-infrared, for example, mid-infrared and FUV. FUV is far ultraviolet because some of the hot stars will emit in far ultraviolet. So they have also used this as an indicator of the star formation rate. And for the same region, they have tried to sample whether there is a molecular cloud there and what is the density of the molecular cloud, surface density of the star formation rate versus surface density of the molecular clouds. And you see that there is a strong correlation across different galaxies. And now, if I look at the structure of molecular cloud, now molecular cloud, I have not shown you a molecular cloud. So is it a blob? Initially, yes, we saw them as blobs, as the kind of globules that I showed you. But when you start going towards the larger scales, recently, only past decade, we have been able to resolve the structure of these molecular clouds into filamentary structures. Now we are finding that filamentary structures are everywhere. And this has happened thanks to Hierarchical Space Telescope, which carried out a large survey of the molecular clouds in our galaxy at far infrared. Now we believe that all the molecular clouds are actually distributed into filamentary structures. And what gives rise to these filamentary structures? Again, people are trying to understand. They actually did a, tried to get the characteristics of these filaments, and surprisingly, they find most of these filaments are longer than 1 parsec. In fact, the width of the filaments also turn out to be something of it's not a very large distribution of widths. The distribution of widths is very narrow. So they are trying to understand what is giving rise to these narrow distribution of the widths of these filaments. And it so happens that the turbulence in the molecular clouds and magnetic fields in the molecular cloud plays a very important role in the way the filaments are formed like this. Okay, and so now you can imagine turbulence in the clouds similar to the turbulence that we experience in the atmosphere, right? And this is a picture of a molecular cloud filamentary structures. As you can see, this is in Aquila, one very close molecular cloud complex. People are trying to understand why should it lead to the formation of these filaments. So this is some I just shown for demonstration of a simulation where people have taken supersonic flows, and if you have supersonic flows colliding, then these can lead to the formation of these filamentary structures, and it can also lead to the formation of stars along the filamentary structures.
Sorry, are filaments more present on the more massive side? You said clouds can be between 10 to the 2 and
yes, yes.
Is it that 10 to the 2 are less filamentary and 10 to the 7
okay.
are more?
So it has to do also how well we can resolve. If I go really the smaller clouds, I can resolve better and I can see the fine structures better if they are closer to us. Once I start going, so we don't have too many large clouds close to us. Again, it's statistics. But the ones which are farther away, that's why these things where they are talking about these, they have looked at the closer ones, were able to do a very good study. But the farther ones, they really need better resolution to be able to study them. So, but we do see now, are all of them of the same even in large clouds, it is not that they are always spherical. We see large, broad filamentary structures also. They are called infrared dark clouds. Now, whether they themselves become smaller striations, we are still waiting to see, because we have not yet reached those resolutions yet, but this is what we anticipate, that they should also become smaller filamentary structures. And overall, they are more or less, very often we see them as filamentary structures. Yes, now, now we understand they are fairly common. Yes, so I'll come to that part. You're saying you're saying that it should have been homogeneous in the beginning and then become like this. We don't know, because you have to, there is turbulence all the time, and something has to feed the turbulence. It's not the turbulence always dies down. So are you talking about the universe?
No, I'm saying like this thing, if I go back in time.
How much are you going back in time?
I'm not sure, but I'm saying like eventually it must have started as
we don't know, because turbulence is something, disturbances which are present, and we cannot say that they were initially very homogeneous and then they became, because somehow turbulence was fed in and they became, we don't know the answer to that yet, because ultimately what we see is what we see now. The rest you get from simulation. So in simulations, probably they would start off with homogeneous and go ahead, but in reality, we don't know. Right now, we see this only. Yeah. Sorry.
Yeah, I was just going to say that the simulations would start off.
Yes. Yeah, simulations usually do that because it's easier for them. And many of these are very simplistic, because if you put in all the complications in the very beginning, it's very difficult. So this
Turbulence must be produced by because of
self-gravity, and then because of the star formation process itself, that again feeds some turbulence into the cloud, which I will be talking about. Okay, so now I have gone from molecular clouds to very large scale, because if you are thinking, where can I find these molecular clouds in the galaxy, right? Because where can I find? I've just talked about phases of interstellar medium in the galaxy, but where can I find them? So as it so happens, galaxies are broadly, you can categorize into these three types, right? The spiral, elliptical, and the irregular galaxies. Now, it is found that molecular clouds are formed, or interstellar medium is dominantly present in the spiral galaxies, in the spiral arms. There is hardly any molecular cloud or interstellar medium, little amount, of course, is there in elliptical galaxies. And in the irregular galaxies also, irregular is like, you can have some, it is intermediate between these two. So now this is just to show you that if I look at this M51 galaxy, Messier 51, this is the optical picture, and you can see these dark lanes, right? That is the dust, which is dust from the interstellar medium, which is obscuring the optical light. So when I look at it in CO, that is the region where I can see that there is interstellar medium, dense interstellar medium is present in the spiral arms of the galaxy, and it is in these spiral arms where the star formation occur. So even in our galaxy, firstly, we are not very sure of structure, but we think it's spiral with various arms. These are believed to be present in the spiral arms of our galaxy. So within the galaxy, in the spiral arms, the size of the galaxy is typically tens of kiloparsec. Okay, I'm going to use this terminology, kiloparsec. Kiloparsec is roughly 3,200 light years. Okay, and within this molecular cloud or interstellar cloud, which is tens of parsecs in size, then please multiply with 3 whenever I say parsec. And within that, you again have these dense regions, which are, you have the molecular cloud, and then within that you have even denser regions, which are the clumps. Within that you have even more denser regions, which are the cores, and it is within these densest regions is where the stars are believed to form. Okay. So this process of star formation, how does it happen? We all know a lot about stars, but how did we gather about the process of star formation? That is because, again, statistics, we are only getting a snapshot of what we are seeing in the sky. Yes. It doesn't occur. It's very little. The most of the stars in elliptical galaxy are old stars, hardly there. The young spiral galaxies are where you will see the stars, young stars, and stars being formed. You are not seeing, stars are not being born in, you see a little amount of dust and all, but stars are not forming in elliptical galaxies. Okay, we can come back to this discussion. I know it will be very long. Can I complete? Huh? No, I did not say about the age. They have been there since a long time. I mean, since the universe formed. I mean, I didn't talk about the age. I'm talking about the stars. I'm talking about the stars. Yes. In the spiral arms, it doesn't mean that you don't have old stars. You do have old stars also, but the young stars are absent in the elliptical galaxies. You have both. Okay. I think I'm really running behind time. I'll try to complete. Okay, so yes, I did not complete this, my last slide. So we know about the star formation process because we have observed them in various phases, and people have tried to understand how the star formation would have evolved, and this was initially initiated by Shue and Adams in 1987. A kind of coherent picture was given for low mass stars less than 8 or 10 times the mass of the sun. So as the molecular cloud is present, within that you have these clumps and cores, and when gravitational collapse is initiated, then what happens, it starts undergoing collapse, and as it is undergoing collapse, you also have density variation. The density is highest at the center and less outside. So therefore, when it collapses, initially that gravitational potential energy is converted to heat energy, but because density is not as high, it can escape, which is isothermal. Initially collapse moves isothermally. Later, as the density increases, then the collapse starts becoming adiabatic. The radiation gets trapped. And once the radiation gets trapped, that radiation heats up more, the cloud even more at the center, and consequently what happens is initially you have this dust which starts subliming, and then you have the molecules dissociate and become atoms, and at even higher temperatures. I'm trying to tell you the whole star formation process in 2 sentences, and at even higher temperatures, the molecules dissociate, become atoms, and as the temperature goes even higher, the atoms get ionized, and you have plasma, and it is in this plasma where you have the fusion reaction occurring, right? So the fusion is that's when you say a star is formed, when the fusion of hydrogen nuclei, that is protons to helium, occurs. But this is what happens at the very center. But what is happening outside? Outside, here collapse is happening, but in most of these clouds, in fact, most of the objects which are present in the universe, because of some amount of torque which was present, there is some small rotation which is occurring, and therefore when collapse occurs, it starts rotating very fast, because as it's collapsing, conservation of angular momentum, it rotates very fast. And when it starts rotating very fast, the collapse cannot happen in the same way in all directions. It is preferentially in a plane which is perpendicular to the axis of rotation, leading to the formation of a disc-like structure. Wherever the rotation is present, it leads to the formation of a disc-like structure. So that is the kind of disc-like structure. This is the envelope where outside it is spherical, but close to it, it's rotating fast, and it is moving in. Material is moving in through the disc. And at the same time, this is something which we are still trying to understand. Some material is launched out along the rotation direction, which is known as jets. What is the exact launching mechanism of jet, and why does it occur? When exactly it occurs, we do not know, but we definitely know that these jets occur, and it occurs even in protostellar objects. So you have this jet which starts coming out, some material is released. It is believed that this process, magnetic field has a very important role to play in the collimation of these jets. And another thing is that it is believed that these jets help in keeping the protostar intact, which leads to the formation of star, because otherwise in the release of the angular momentum, otherwise it will be moving very fast and star would not form. So, but exact launching mechanism we do not know yet completely. And so what is left at the center is that is a young star which has just formed, that is known as main sequence star. A main sequence star is a star which is fusing hydrogen to helium like our sun right now. And over time, this jet envelope, everything dissipates. And it is in this disk is where planets form. You have these small accumulated masses, which are called planetesimals, and over time that accumulates more and more mass, and that becomes the planets. So therefore, you will see these planets are all moving in one plane, and that is because they formed in the protostellar disk along with the formation of the star. Okay, I've also given the scales. Now, the way the massive stars, I've talked about low mass star formation because that is fairly understood in terms of phases. When I talk of stars of mass which are greater than 8 to 10 times the mass of sun, it so happens that there are other processes that start coming into picture. I will not go into them because of in the interest of time, but what I will tell is that these stars, massive stars, are usually always found to be formed accompanied by lots of other low mass stars. That is, they are formed in clusters, and they are usually found at the centers of the clusters. Now, I don't know if you have this question, in what ratio are the masses of different stars formed? It so happens that the low mass stars are formed in much larger numbers as compared to higher mass stars, and if one has to look at the distribution, this distribution comes empirically. Okay, because we do not have a theory from which the distribution comes out. People try to fit that into it's a constraint in some sense. It's that we have an inverse power law is what we find. That is, the massive stars are very rare compared to low mass stars. So if you're very happy about sun and its mass, then you should know that this is one of the most common type of stars which is present in the galaxy. It's not special in any way. So this is how I described the low mass star formation. You had this clumpy molecular cloud, and then you have this collapsing core, and then you have this warm core, you have the jet, and then you have the star with the disk and star. But if I look at massive star formation, at individual massive star, all these processes occur on much faster time scales because the amount of fuel or the mass which is there is much more. So the time scales over which a jet would be released from a massive star or a disk would be formed is much shorter compared to a low mass star. And in this case, massive stars greater than 8 to 10, they start giving out significant amount of ultraviolet radiation which can ionize the surroundings. And these surroundings, once they get ionized, what you are left with is plasma. So these are known as H2 regions, what you see here, that denotes H+. So these are these H2 regions, which is the ionized gas, and in this plasma, because of the various processes, you can detect them in radio. So you can use H2 regions also to detect the location of massive stars. So I'll come back to some of these aspects as we move along. Yeah.
Are these jets expected to form always?
Yes, more or less, always. We find them, a really large number of jets, not jets, people look at them in terms of outflows. I'll come to that, which is a kind of second order effect. We don't always detect the jet, but we detect an indirect evidence of that. When it pushes, the jet is pushing the surrounding material out, we call it outflow, and they are seen everywhere.
This formation is very prominent in the case of high mass stars.
Yes, it is there everywhere. It is universal in star formation. Always you will have low mass, and high mass you will find jets and outflows. So I will come to this aspect of what an outflow is, because we cannot always detect jets. We detect something called outflows, which indirectly tells us there's a jet and a disk. So I'll come to that aspect.
The formation of the observation to the
yes.
It is always going into this disk-like structure.
It has to be, because otherwise gravity is a radial force, right? So if the symmetry is broken and you're seeing a jet, there has to be a disk associated with it. Or if there is a disk, then there has to be a jet. And in fact, nature is such that this is not the only region where you have jets and disks. You have them around a multitude of other objects, even on galactic scales. Even in galaxies around the central supermassive black holes, you have jets and disks, which are seen even around some kind of neutron stars and so on. So this is there everywhere. It's a universal phenomenon, but only the kind of conditions over which they are launched may be different.
But if you look at the individual structure of stars, those are spherical.
They are spherical, but not really spherical. Disk structure of star, yes. but around it the matter which is going in, that goes in through the disk, and this matter comes out. It's from the disk, it's not coming out from the star. It's the accreted matter which is going in is getting funneled out, okay, before the star formation. Okay, so I don't know whether I should go into this. This is for understanding the massive star formation. There are various models. According to one model, which is monolithic collapse model, the massive star also collapses and forms in the same way that I talked about the low mass star. Okay, but in this case of massive stars, the rate at which the matter moves in and the rate at which the outflow comes out, those rates will be much, much larger. Okay. Now there is, since these massive stars are always found along with clusters, that is other members of stars, that means the other fragments or other cores around it should also be collapsing to form stars, correct? And so there is this alternative theory which is proposed, which is known as competitive accretion. A rich man keeps getting richer and a poor man keeps getting poorer. So the massive star at the center is the rich person who starts pulling material from the surrounding young protostars which are accreting matter, right? They are all within the one cloud. So everybody is trying to accrete matter. But this is more massive. It starts pulling in from the other regions also. This can explain the presence of massive stars at the centers of clusters, and it can explain the formation of clusters. So this is the theory of the competitive accretion, where the mass is gathered in the massive star during the process of star formation. And then there was this very interesting theory. Now it is almost discounted and we don't believe it anymore. But there was a theory which said that the massive stars are formed because these low mass stars can come together, and where the stellar densities are very high, they can coalesce and merge. But if this process were to occur, a huge amount of energy should be given out, which we don't see in nature as much. Only towards Orion molecular cloud, we see some indications, and that's what gave rise to this kind of theory, but now it is no longer considered as active contestant in the formation theories of massive stars. So now how does this massive star formation or star formation in general relate to these filamentary structures, right? We were talking about molecular clouds, filamentary structures. So where in the filamentary structures are these young stars, massive stars formed? And it so happens that these filamentary structures, although they can also coalesce together and form something called a hub. So you have a hub and filamentary structures, and it is found these hubs are the region where massive stars are usually formed. You can also have stars forming in the filamentary structures themselves, but these hubs always have a rich cluster where a star is forming. So this is a massive dense core in the center, which is shown by this picture, and in this massive dense cores you can have these other small regions which are undergoing collapse. This is starless core, it has not yet formed star, and then at some stage when it starts it undergoes when it starts becoming adiabatic in some sense, you say that it reaches some sort of equilibrium, the collapse and the heat, that's known as the hydrostatic equilibrium. That's when we say that this is a protostar. So this it has not yet formed a star. And in this protostar, as time goes by, this protostar by itself will undergo collapse and lead to the formation of star. This is one particular region in serpents where they have actually seen accretion happening along with the filaments, because this is the densest region. This is the deepest part of the potential well. So this is where matter starts flowing in, is what has been shown also from observations. Okay. Now locating infant stars, we know now, I think you will be able to understand most of what is written here. So how do I locate infant stars? Where do I locate that stars are being formed? First and foremost, I look for high density clumps and cores in molecular clouds. Then I look for protostellar outflows. Where can I find these protostellar outflows? I find them using millimeter and infrared. Then regions of H2 regions are ionized gas regions. I can look for those. I can look for embedded protostar or cluster. I can look because this protostar now heats up the surrounding, so the nebula surrounding it also starts to glow, so I will see nebulosity. Then wherever there is hot gas, which I can trace using excitation, high excitation molecular lines, or shocked gas, or spectral energy distribution. I'll go over these a bit quickly. So this is the location of, again I am showing the aquila, the filamentary structures which I showed. What is shown here, the black dots represent pre-stellar cores. That means these have not yet formed stars. They have identified such cores. And what you see in magenta are the cores which are forming stars, the protostars. So people have identified this, used this technique, locating high density to find out where stars are being formed. So what I'm going to do now is quickly tell about these techniques and show examples. Then protostellar outflows. I talked about jets, but this jet is this high velocity material which is coming out from very close to the star. Now, because all this happens in a dense molecular cloud and it is very high velocity, it pushes the surrounding material and takes it along with it. That's known as the entrainment of material. So now, if this is the protostar, some material is pushed this side and some material is being pushed that side, the associated molecular cloud. Now, if it is tilted, what would you see? Some part is going that side and some part is coming towards you. So you actually see the blue and red motions. That's known as the outflow. So we use Doppler motion of the spectral lines to be able to identify the lobes of these molecular outflows. And this is a very, very common technique which is used by in star formation to understand this, to locate the outflows, and therefore there has to be a jet associated with it. That is what is shown in this cartoon picture here. So this is again showing that what you see as the blue and the red shows the red shifted emission and blue shifted emission from a cluster of stars. So you see a large number of outflows are there. You see this blue and this is red. So this is the geometric center and this is where the protostar is driving the outflow, and a large number of them you can see. Okay. And by the way, I should also add that this 4.5 micron, this is a mid-infrared emission, and here also there are some CO lines at 4.5 micron which are used to trace outflows. So that is shown in the green there. Sorry, I went a bit ahead. So the green thing you see here, that shows if there is extended emission, it shows that there are outflows in mid-infrared. Now this is actually the jet you are seeing, shocked gas from the jet at optical and infrared, because as the jet moves through the medium, it can shock the medium, which can at high temperatures, then it can start emitting in optical light and in certain spectral lines. And here very clearly you can see the effect of the jet. So when it interacts, the jet interacts with the interstellar medium. When it comes across a dense interstellar medium, it shocks that. And these are known as Herbig-Haro objects, after Herbig and Haro who first found them. And you can see that in some cases you may not be able to see the jet till it encounters this. But in some cases you are able to see the entire jet because it is able to shock and keep moving along. So these are some of the Herbig, that's why this HH represents that, Herbig-Haro 111. We have a catalog of such objects. And then you have, this is another such jet, and here you don't see the jet really, isn't it? You just see the edges. From this you know that there is some protostar which is exciting this, okay? And this, for example, in the optical you could see, but in you could not see the other side. You could see in optical some shock-like structures. So they have gone, this is in the optical light. So they went into the radio wavelengths using ALMA, Atacama Large Millimeter Array, and tried to, and there they were able to see the other part of the outflow also. So then they are able to sample the entire jet. And they were even able to locate very clearly which is the exciting star and study it in detail. Now we in particular have been interested in protostellar jets, but we have been using radio measurements to be able to look at them. So we have been using GMRT, Giant Meter Wave Radio Telescope, located at Pune, and where we have sampled at lower radio frequencies the Herbig-Haro objects, a large number of this which is coming from some object in here, and we were able to, this is the largest, one of the larger, at least currently it is the largest jet from a massive object in our galaxy. And at lower frequencies we were able to sample, the shocks are so strong that they the ionized gas there the magnetic field gets compressed and it gives rise to synchrotron emission, because the electrons can get relativistic in this region and it emits in synchrotron, and that synchrotron is higher at lower radio frequencies as compared to higher radio frequencies, so we can sample them much better than what people at higher radio frequencies with very large array in USA can. So this was for the first time shown very clearly that there is synchrotron emission from this very different parts of this jet is what we had shown. So what I'm trying to say is we can also use radio here. With one of our students, Sri Lakshmi, she is looking at this in the near infrared. This has not been sampled. We are using other traces of shocks and jets in near infrared, like the excited iron line and so on, and we are trying to look at the jet. This is the jet. You see this orange part, that is the emission that we have detected in near infrared, and we are working on this and trying to understand. We have also done some simulations to understand the radio emission from these jets. I won't go into details, but basically there was not much literature that we found that explained how the synchrotron emission can be explained in terms of the jet parameters or the magnetic field which is present there and so on. So we carried out some numerical simulations in order to understand what is the what are the various jet parameters, what's the inclination, what's the, how the density parameter changes, how the ionization fraction changes across the jet and so on. So the idea was to use the observations that we have got and using these simple simulations come up with various parameters that can fit these observations. So this is of course done published this year. Now looking from protostars, moving on to other kind of objects which are used to pinpoint stars, and they are H2 regions, that is regions of ionized hydrogen around massive stars. So ionized gas around young massive stars can be looked at in radio. So you see this region in W49, this is in radio. All this region has one or more massive stars which are embedded within them. And as you can see now, they have different shapes. Okay, and these shapes tell us about the how the density of the matter is in the vicinity of this star, because ionization happens according to density. Over time it will ionize the surroundings, where there is, depending on how the density distribution around it, the ionization also will happen accordingly.
What is the reason these clouds emit in radio? I would expect that recombination will give in the optical, right?
Yeah, recombination is in optical, but this is thermal Bremsstrahlung. Free emission, yes. So this is the free the coming from in H2 regions you have thermal emission, you don't have non-thermal emission, and this thermal emission is because of the acceleration of the electron in the presence of the proton. So we have also been studying a number of H2 regions, and here I've just listed out some sample of different kinds of H2 regions that we have studied with the Giant Meter Radio Telescope over the last few years. Then another way to locate the infant stars is to look at embedded protostars or embedded clusters, as I told you. So once you see a cluster like this is of course you can look at it directly in near infrared. In optical also, in radio you can obviously locate, but in optical also, the moment you start seeing something like this, or in near infrared you start seeing something like this, you know that this is a very young cluster sitting there, and then you can go on to try and study more about this cluster. So we have looked at some of this. We also carried out some simulations in order to understand how many cluster members should be visible to us, because you can make assumptions about what is the how the distribution of stars when they were formed, that's known as the initial mass function. You can make assumption about how the star formation occurred. Was it a burst of star formation or did it happen over some time scale? So all these goes in, and other things that goes in terms of assumption is how the protostars are going to evolve with time. We have taken all this into consideration and put it within a molecular cloud, and then seen that if I have the sensitivity of one of the telescopes, say Spitzer, how many stars I will be able to detect if I distribute them randomly within a cloud. And that was what the simulations we had done. These were the observables that we put into simulations based on the observations, and these are some assumptions that went into it, and based on that we came up with, we can tell more about what happened in the past. Okay, but again, this is again various simplistic models that we took in. Among these, which one fits the best is what we have done. So here was, I won't go into detail, but these are the various power law distributions. There are various kinds. Then whether the star formation rate is uniform or not, we had taken various models. When did the star formation begin? And when it ended, how long it lasted, and so on. And based on that, this is the number of cluster members which are according to brightness distribution. So this is the brightness of the cluster members as we see it, and this is the number of cluster members which are seen in that brightness bin. So based on these simulations, we then tried to fit with what we are actually seeing. And based on the one which is the closest fit, we say probably this is what could have happened. But of course, as I'm telling again, these are simplistic I mean, if you actually, but it is simplistic, but at the same time, we do not know what happened in the past. So in that sense, it helps us understand how things probably would have happened. Okay, so other ways to locate the infant stars are to look for areas of shocked gas, because when the H2 region is expanding, because H2 region is ionized gas, so it expands over time, right? Because the UV photons are coming out continuously, it ionizes, so the region is expanding, and this ionization front can also, if this disturbance moves faster than the speed of sound, then it can shock the medium around it, and there you can find certain molecules which get excited. They are known as polycyclic aromatic hydrocarbons, which emit at 8 microns in mid-infrared. So you will see such structures. These structures you can also see around supernova remnants, right? Where you see this nice supernova. I don't know if you've seen pictures of supernova remnants, but those are also shock structures. But here are also shock structures which are like bubbles like this. But then how do you distinguish between these kind of structures and supernova remnants, for example? These are located within molecular clouds, and close to where the excitation is, you will find this dust kind of emission at mid-infrared, which you may not see so clearly in supernova remnant. There everything will be pushed out. And this is one such region where we had studied, again, here it's a 3-color composite image where the 250 micron far infrared is shown in blue, Spitzer 8 micron is shown in green here, that is the excitation from the PA molecules, and you have the dust emission at mid-infrared 24 micron in red. Where here similarly we have created a 3-color composite, and I just wanted to emphasize about this bubble structure that we had seen. Then you can also locate with regions where the gas temperature goes very high, that a number of molecular lines now close to a protostar, because of the radiation which is coming from inside, okay, star may not have been formed. That excites the molecules which are present outside, because it has not yet formed a star. Now there you can have a number of complex molecules. When they start getting excited, you will have high excitation transitions you will see from there, which you will not see from a normal molecular cloud, because then the electrons get excited to very high energy levels of these complex molecules. So this is one such, and these are known as hot molecular cores. So this is one such spectrum of the hot molecular core. And this shows that how at these temperatures which molecules can get excited, and at these temperatures which molecules you can see, and you can also see which part, how close it is to the star, you can locate these kind of molecules. And this is the spectrum. This is a schematic. We had also worked on hot molecular cores where we had seen we had seen ammonia lines, and we had seen methyl cyanide lines, and towards a molecular core, G24.78, which is shown here. So if you see this, the reason I am showing them as contours is because this is at 1.4 millimeter. You can also show a picture, but I have a contour image here. These are lines of same intensity. There were 2 cores. I was studying this particular core, A2, and towards this we found that there's a hot molecular core, and we looked at the distribution. This is, now this actually represents the position and the velocity. We are also trying to look at the velocity distribution in the vicinity of this core, and trying to simulate that as well using a model for a disk and so on. Now the final thing for locating young infant stars is this. This is known as spectral energy distribution. Sometimes you may not be able to get good images. So what we do is we take the brightness of the stars at different wavelength bands and we plot it. So we are plotting brightness of this object versus the wavelength, that is known as the spectral energy distribution. And you can see this is the initial collapse phase, when you are having the outflow phase. This is broadly. And you can see how the spectral energy distribution to some extent can be used to identify these phases. This is when it is very cold. Okay, because it is just in the collapsing phase. So it's like a black body, a cold black body, and then it starts warming up, and you can no longer think of it as a spherical thing. There's also a disk which has a temperature gradient. So you can fit the spectral energy distribution with a disk and a protostar in the center. And then as it evolves with time, the disk is going to dominate, the envelope has gone, and there's a temperature gradient in the disk which shows up in this form, and this is the star at the center. So you will see, finally what you see, you can model it as a combination of the various components which are present very close to the star. And this is of course the debris disk. You have the star and just a very remnant disk. This actually shows a number of young stellar objects, how the data is used to find out the stage in which the star is formed, what is the mass of the central star, what is the disk, what is the inclination of the disk. So there are, Robitaille actually worked on a number of such models, hydrodynamic models, and he has actually given these models that you can fit these models to data if you have across the full electromagnetic spectrum. Now that completes understanding how to locate massive stars. I have completed 1 hour. I have some time, some 10 minutes. Do I? Yeah, I'll try to wind up quickly. Okay, so this massive stars, not only, they also start affecting the surrounding interstellar medium, obviously, because you are having all this radiation which is going out, you have this protostellar jets and outflows which are going out, that starts affecting the medium around it. So we also study the effects, because, and then it can either, if there is another dense cloud there, it can trigger the collapse of that, or it can lead to dispersal of the molecular clouds. All these things happen, and in the vicinity of the star, how the feedback effects of the star can form, that can also be studied. So here, for example, is animation showing that this is where the younger cluster is, and this purple thing which you are seeing is the velocity of the, indicates the gas distribution around it. Now if you look at this animation very clearly, you will see that whichever part is dark is where the dense gas is, and this part, the gas, you don't see as much dense gas anymore, because from here the dense gas is now pushed away. This is where the star formation has occurred. So the dense gas is now pushed away, and that is what this animation is showing. So there are various feedback effects. I will not go into the detail, but what I will tell you, and what are these feedback effects? Protostellar outflows, the output of far ultraviolet radiation, winds from these young massive stars, and so on. And in fact, the massive stars evolve so fast that they can even lead to the formation of supernova, and which can disperse the molecular cloud before a low mass star has completed its evolutionary phase also. So even a supernova remnant within a supernova can occur within the molecular cloud, and it can affect the molecular cloud a lot. So massive stars affect the surrounding interstellar medium much more than low mass stars. So we in fact had found once a supernova remnant in a molecular cloud, and using optical and radio we actually showed that there is a molecular cloud here, but we also found a remnant of supernova that would have occurred long ago. Now, in spite of all that I have told, a number of, the devil is in the details, right? So a number of questions remain. Like we know roughly how things are happening on various scales, but we don't know the fine details. And I have listed some of these questions here. I'm sure you have much more. So what triggers the initial collapse? Okay. We have some answers. People are trying to answer them. We can discuss them at the end if you are interested. We can discuss all of these if required. And what factors affect, because molecular cloud, I am saying it leads to this dense cores formation. Within that, again, you have this dense. So that is known as fragmentation. So somewhere some fragments are there. What led to the because that leads to the formation of cluster. What led to this formation of these fragments? And how do the various pressures, thermal, turbulent, magnetic pressure, how do they evolve over time, and how do they contribute to the various processes of star formation? Because some of these can resist the self-gravity, but yet the stars are being formed. What is the size of the protostellar disk, and how does it evolve with time? What is launching mechanism of jets? At what stage does it occur? When does it stop? We do not know. Accretion mechanism of the protostar, is it previously accreted or is it accreting over time? The different models that I told you about, massive star formation models. What's the time scale of star formation? Is it happening on free fall time scale or is it slower than that because of the resistances of various, due to various other pressures? And what is the star formation efficiency? What fraction of the molecular cloud goes on to form stars? Is the full molecular cloud, is all the material used up? No, it is not. But then what fraction and how is it decided? So these are various questions which still remain. If you are keen, I can do this for 5 minutes, otherwise we can stop here. Yeah, I should do. Okay, I'll just do it couple of minutes. Okay, so we are actually looking forward to James Webb Space Telescope because it is going to operate in mid-infrared. It is very large, right? And mainly you can peer into the molecular clouds at near and mid-infrared wavelengths. It uses space-based mid-infrared measurements. The reason I'm emphasizing on space is that it is very, very difficult to do mid-infrared measurements from ground because atmosphere absorbs. So you can't do it. You can do marginally only up till certain wavelengths or at certain wavelengths, but most of it is absorbed. But of course, once you are in space, there's no such limitation. You can do across all the mid-infrared band. Then you can use good instruments, you can use imaging, you can use spectroscopy, and you can visualize details close to the protostar. And this is definitely a progress from Spitzer Space Telescope, which also operated in mid-infrared but was much smaller, 85 centimeters in size. Okay, so that way you will be able to see with the James Webb Space Telescope very, very faint objects. You can detect very faint emission. And just to give you an idea of the resolution, that means if the resolution is 0.1 arc second at 5 micron, which means at a distance of 150 parsec, or let's say 500 light years, you can see structures of 15 AU. AU is roughly the distance between sun and earth, typically. So 15 times that you can see at 450 light years. So that just gives you an idea of how much close you can go and see what is happening. So we are expecting it to usher in a new era in terms of the details that we can see close to protostars. So this is, of course, a picture you have seen within a couple of months, and that's again the Horsehead Nebula, right? But this is in mid-infrared. This is not in mid-infrared. This is also this is optical and near infrared, but with James Webb Space Telescope, we are expecting to see much more beautiful pictures very close to protostars. And this is just this was just their initial advertisement in some sense of what JWST can do. So the kind of instruments it has, it is going to work from 0.6 micron till around 28 micron. That is quite some bit. And it has a number of instruments. It has an imaging instrument. It has a spectroscopy instrument. I won't go into the details, but I will tell you that, see, as you can see, one of the main aims is to study protoplanetary disks, go in really close and to see what happens, try to answer those questions, and also see how planets get formed in some sense, and also try to image extrasolar planets as well. And so using this, you can spatially resolve protostars, disks, envelopes, and outflows. You can characterize them, all the conditions of these using spectroscopy, and you can sample the mid-infrared spectral energy distribution. Till now we were relying only on models, but now you will actually be able to get data, and that will help you understand much better what is happening rather than just relying on models in the absence of data. So I think more or less that's about all. This is the summary. I will not take time on this. I will just show some of the group members in the past few years, the PhD students and some of the master students who have worked with me on various aspects of star formation. And we have worked on molecular clouds, H2 regions, we have worked on embedded clusters and protostars and jets. And so I'll stop with that. Thank you for your attention.
Thanks for that very fascinating look into the birth of stars. Any questions?
Cluster simulations and what exactly does one does and what level do you really
See, what we do is first we define the size of the cloud, and then based on that, based on an IMF, you know IMF, right? Initial mass function. So we, as I told you, this is something which is determined empirically. That means the low mass stars are formed much in number and high mass. So we need to put in protostars in a certain distribution of numbers. We randomly put them in there and then allow them to evolve. Yes, randomly, yes, we randomly put in there and allow them to evolve. For that also there are models to see how they evolve with time. So at a certain age, what is the emission from each of these and whether it will be visible to us now, because it has to pass through this cloud. They are located randomly, right? So the ones behind may not be able, may not be able to see. We run this simulation not once, but it's a Monte Carlo kind of thing. We run it thousands of times and then try to get a kind of mean spectrum, median spectrum, and then do that. So that's why you had, even with the data, even with the models, we have quartiles and so on. So we put in various things from observations. What is the size of the cloud? What's the most massive star? What's the luminosity? Plus we put in star formation history and the evolution from models which are known. Put in these two together and see how many cluster members should I be able to see at this age today, if this is there. So that way I'm probing into the star formation history. Okay. We were talking a lot about this, right? Yes, so the main difference is in the scales and the surroundings. In the AGN case, for example, that's the mass scales there are very, very different. These are very teeny-weeny compared to that supermassive black holes, right? Secondly, the kind of conditions there, those are relativistic, ultra-relativistic, which is not the case here. And that relativistic effect comes in because there's hardly any material where they are ejected. Whereas here, they are ejected into molecular clouds. So there's a lot of medium around it. So there you will only consider those relativistic mechanisms that go into understanding what is the emission. Here, when you want to look at how the jet and the outflow and things evolve, you need to see not only how the jet evolves, but the shocks it creates. And in these shock conditions, how the atomic and molecular lines will get excited, how they get slowed down, what are the emission mechanisms there. So it becomes more complex than what you had in AGNs. It's not known even in AGN jets, right? Yeah. So those kind of things are there even here. But do we know for certainty? Like there are models, right? Here also there are models. It's not that it's not there. I didn't talk about them. Just as you had there, here also we have X-wind and disk-wind models. Where the jet is very close to star or whether it's coming from the disk. But exact mechanism, what is the role of the magnetic field in helping it launch and collimate? Those details are not known even here. That is not known, I think, for jets in general. That is the mechanism that I'm talking about.
Okay, I had a question in connection to that.
Yes.
So like in the AGN jets context, there has been studies done where they find that there is some kind of correlation between the jet power and the disk. There is a connection between the luminosity of the disk and so on, depending on like what the magnetic field is. And so is there something similar?
People are trying, but you can't resolve the disk here very well because it's all embedded in here. So what they are trying to do is they are trying various other things to understand if they are able to find the disk and they are able to see the jets. Mostly you don't see the jets very often. As I said, you see outflows. From that, the jet parameters is not trivial because what you will be seeing the molecules which have emitted from the entrained material outside. From there, if you want to go to what exactly is the power of the jet is not easy. So again, people use models saying 10% of the mass is going here. Of the accretion is being going there, but that is also not very well known. People have tried it with low mass objects because low mass star forming object, protostars, because their things are more visible and there are correlations. But once you start going to massive star regime, things become very fuzzy. These are formed in clusters, deep embedded within molecular clouds. They're all located very close to each other. The mechanisms could be very different. So in low mass side, things are more or less clear regarding these correlations, but not as much towards a massive star regime.
Is there a correlation
between the disk accretion and yes, people have found, they have tried to relate the accretion rate with the outflow rate using certain lines which are accretion traces and which are outflow traces. So there are, and they find it to be related. Yes.
Any other questions? All right. If there are no more questions, let's thank Sarita again.
Thank you.